In Part 4 of Lecture 4, we will discuss threads in Windows 8. An application consists of one or more processes. Each process provides the resources necessary to execute a program. A process has a virtual address space, executable code, open handles to system objects, a security context, a unique process identifier, environment variables, a priority class, minimum and maximum working set sizes, and at least one thread of execution. Each process is started with a single thread, often called the primary thread, but can create additional threads from any of the threads. A thread is the entity within a process that can be scheduled for execution. All threads of a process share its virtual address space and system resources. In addition, each thread maintains exception handlers, a scheduling priority, thread local storage, a unique thread identifier, and a set of structures the system will use to save the thread context until it is scheduled. On a multiprocessor computer, the system can simultaneously execute as many threads as there are processors on the computer. A job object allows groups of processes to be managed as a unit. Job objects are nameable, securable, shareable objects that control attributes of the processes associated with them. Operations performed on the job object affect all processes associated with the job object. Examples include enforcing limits such as working set size and process priority, or terminating all processes associated with a job. A thread pool is a collection of worker threads that efficiently execute asynchronous callbacks on behalf of the application. The thread pool is used primarily to reduce the number of application threads and provide management of the worker threads. A fiber is a unit that must be manually scheduled by the application. Fibers run in the context of the threads that schedule them. Each thread can schedule multiple fibers. In general, fibers do not provide advantages over a well-designed multi-thread application. However, if fibers can make it easier to port applications that were designed to schedule their own threads. From a system standpoint, a fiber assumes the identity of the thread that runs it. For example, if a fiber accesses thread local storage, it is accessing the thread local storage of the thread that is running it. In addition, if a fiber calls the exit thread function, the thread that is running it is the one that exits. However, a fiber does not have all the same information associated with it as that associated with a thread. The only state information maintained for a fiber is its stack, a subset of its registers, and the fiber data provided during fiber creation. The saved registers are the set of registers typically preserved across a function call. Fibers are not preemptively scheduled. A thread schedules a fiber by switching to it from another fiber. The system still schedules threads to run. When a thread that is running fibers is preempted, its currently running fiber is preempted but remains selected. User mode scheduling, or UMS, is a lightweight mechanism that applications can use to schedule their own threads. An application can switch between UMS threads in user mode without involving the system scheduler and regain control of the processor if a UMS thread blocks in the kernel. Each UMS thread has its own thread context instead of sharing the thread context of a single thread. The ability to switch between threads in user mode makes UMS more efficient than thread pools for short duration work items that require few system calls. UMS is useful for applications with high performance requirements that need to efficiently run many threads concurrently on multiprocessor or multi-core systems. To take advantage of UMS, an application must implement a scheduler component that manages the application's user mode scheduling threads and determines when they should run. Windows 8 changes their traditional Windows approach to managing background tasks and application lifecycles. Developers are now responsible for managing the state of their individual applications. Previous versions of Windows always gave the user full control of the lifetime of a process. In the classic desktop environment, a user is responsible for closing an application. A dialog box might prompt them to save their work. This holds true in the desktop mode of Windows 8. In the new Metro interface, Windows 8 takes over the process lifecycle of an application. Although a limited number of applications can run alongside the main app in the Metro UI using the Snap View functionality, only one store application can run at one time. This is a direct consequence of the design. Windows 8 live tiles give the appearance of applications constantly running on the system. In reality, they receive push notifications and do not use system resources to display the dynamic content offered. The foreground application in the Metro interface has access to all of the processor, network, and disk resources available to the user. All other apps are suspended and have no access to these resources. When an app enters a suspended mode, an event should be triggered to store the state of the user's information. This is the responsibility of the application developer. For a variety of reasons, whether it needs resources or because an application timed out, Windows 8 may terminate a background app. This is a significant departure from the Windows operating system that preceded it. The app needs to retain any data the user entered, settings they changed, and so on. That means you need to save your app's state when it's suspended, in case Windows terminates it, so that you can restore its state later. When the app returns to the foreground, another event is triggered to obtain the user state from memory. No event fires to indicate termination of a background app. Rather, the application data will remain resident on the system as though it is suspended until the app is launched again. Users expect to find the app as they left it, whether it was suspended or terminated by Windows, or closed by the user. Application developers can use code to determine whether it should restore a saved state. Some applications, such as news feeds, may look at the date stamp associated with the previous execution of the app and elect to discard the data in favor of newly obtained information. This is a determination made by the developer, not by the operating system. If the user closes an app, unsaved data is not saved. With foreground tasks occupying all of the system resources, starvation of background apps is a reality in Windows 8. This makes the application development relating to the state changes critical to the success of a Windows 8 app. To process the needs of background tasks, a background task API is built to allow apps to perform small tasks while not in the foreground. In this restricted environment, apps may receive push notifications from a server, or a user may receive a phone call. Push notifications are template XML strings. They are managed through a cloud service known as the Windows Notification Service. The service will occasionally push updates to the user's background apps. The API will queue those requests and process them when it receives enough processor resources. Background tasks are severely limited in the usage of processor, receiving only one processor second per processor hour. This ensures that critical tasks receive guaranteed application resource quotas. It does not, however, guarantee that a background app will ever run. Windows process design is driven by the need to provide support for a variety of operating system environments. Processes supported by different operating system environments differ in a number of ways, including the following: how processes are named, whether threads are provided within processes, how processes are represented, how process resources are protected, what mechanisms are used for interprocess communication and synchronization, how processes are related to each other. The figure on the slide illustrates the way in which a process relates to the resources it controls or uses. Each process is assigned a security access token, called the primary token of the process. When a user first logs on, Windows creates an access token that includes the security ID for the user. Every process that is created by or runs on behalf of this user has a copy of this access token. Windows uses the token to validate the user's ability to access secured objects or to perform restricted functions on the system and on secured objects. The access token controls whether the process can change its own attributes. In this case, the process does not have a handle opened to its access token. If the process attempts to open such a handle, the security system determines whether this is permitted, and therefore whether the process may change its own attributes. Also related to the process is a series of blocks that define the virtual address space currently assigned to this process. The process cannot directly modify these structures, but must rely on the virtual memory manager, which provides a memory allocation service for the process. Finally, the process includes an object table with handles to other objects known to this process. The figure shows a single thread. In addition, the process has access to a file object and to a section object that defines a section of shared memory. The object-oriented structure of Windows facilitates the development of a general-purpose process facility. Windows makes use of two types of process-related objects: processes and threads. A process is an entity corresponding to a user job or application that owns resources, such as memory and open files. A thread is a dispatchable unit of work that executes sequentially and is interruptible, so that the process can turn to another thread. A Windows process must contain at least one thread to execute. That thread may then create other threads. In a multiprocessor system, multiple threads from the same process may execute in parallel. The table shown on the slide defines the thread object attributes. Note that some of the attributes of the thread resembles those of a process. In those cases, the thread attribute value is derived from the process attribute value. For example, the thread process affinity is the set of processors in a multiprocessor system that may execute this thread. This set is equal to or a subset of the processor affinity. Note that one of the attributes of a thread object is context, which contains the value of the processor registers when the thread last ran. This information enables threads to be suspended and resumed. Furthermore, it is possible to alter the behavior of a thread by altering its context while it's suspended. Windows supports concurrency among processes because threads in different processes may execute concurrently, appear to run at more or less the same time. Moreover, multiple threads within the same process may be allocated to separate processors and execute simultaneously, actually running at the same time. A multi-threaded process achieves concurrency without the overhead of using multiple processes. Threads within the same process can exchange information through their common address space and have access to the shared resources of the process. Threads in different processes can exchange information through shared memory that has been set up between the two processes. An object-oriented multi-thread process is an efficient means of implementing a server application. For example, one server process can serve a number of clients concurrently. An existing Windows thread will be in one of 6 states shown on the slide. The ready state. A ready thread may be scheduled for execution. The kernel dispatcher keeps track of all the ready threads and schedules them in priority order. Standby state. A standby thread has been selected to run next on a particular processor. The thread waits in this state until that processor is made available. If the standby thread's priority is high enough, the running thread on that processor may be preempted in favor of the standby thread. Otherwise, the standby thread waits until the running thread blocks or exhausts its time slice. Running state. Once the kernel dispatcher performs a thread switch, the standby thread enters the running state and begins execution and continues execution until it is preempted by a higher priority thread, exhausts its time slice, blocks, or terminates. In the first 2 cases, it goes back to the ready state. Waiting state. A thread enters the waiting state when it is blocked on an event, for example, input-output. It voluntarily waits for synchronization purposes, or an environment subsystem directs the thread to suspend itself. When the waiting condition is satisfied, the thread moves to the ready state if all of its resources are available. Transition state. A thread enters this state after waiting if it is ready to run, but the resources are not available. For example, the thread's stack may be paged out of memory. When the resources are available, the thread goes to the ready state. Terminated state. A thread may be terminated by itself, by another thread, or when its parent process terminates. Once housekeeping chores are completed, the thread is removed from the system, or it may be retained by the executive for future reinitialization.